Imagine for a moment that you are holding a glass of water. You tilt your hand and the glass slips. It falls. It strikes the floor and shatters into a dozen pieces, water spreading in a quiet silver pool across the tile. You know, instantly and without any deliberation at all, that this event is moving forward in time. No one has to tell you. The information is written into the event itself, a kind of invisible signature that every human being, in every culture, across every era of recorded thought, has always been able to read. The glass falls, it breaks, it does not reassemble. But here is where the universe begins to reveal one of its most unsettling secrets. The laws of physics, those fundamental equations that describe how matter and energy move and interact at the deepest levels of reality, contain no such signature. They are written in a language that carries no preference for one direction of time over the other. If you filmed that falling glass and played the footage in reverse, the equations of classical mechanics would look at the time-reversed version and declare it perfectly legal. Every particle obeying Newton's laws, every force behaving exactly as it should. The mathematics does not blink. And yet you would know, the instant you saw it, that the reversed film is wrong. The shattered glass does not leap from the floor and reconstitute itself in your hand. Water does not spontaneously gather from a spreading pool and climb back into a container. Heat does not flow from a cold room into a warm cup of coffee to make it hotter. These things simply do not happen, and we have never seen them happen, and we carry such a deep certainty of their impossibility that the reversed film seems almost comical, like a joke the universe is playing on the laws it supposedly follows. Welcome to Deep Space Intelligence. I am Liam. This channel is very new, and every like and subscription truly helps us grow and bring you even deeper, more powerful research. Thank you in advance for every like and follow. This is the arrow of time, and it is one of the deepest and most genuinely unresolved mysteries in all of physics. Not because scientists lack imagination, and not because the tools of modern research are insufficient, but because the mystery cuts directly to the foundations of what physical law is and what it can actually tell us. The equations that govern the universe appear to be neutral on the question of direction, and yet the universe itself emphatically is not. Something is producing an arrow where the mathematics insists none is required. Something is forcing time to flow forward, and the question of what that something is has tormented some of the greatest minds in the history of science for more than a century and a half. To feel the full weight of this puzzle, you need to understand just how deep the symmetry runs. It is not a quirk of one equation or one theory. It runs through virtually the entire architecture of fundamental physics, and that is what makes it so strange and so stubborn. Start with classical mechanics, the framework Isaac Newton gave us in the 17th century. When Newton wrote down his laws of motion, he described a universe governed by forces and accelerations, where every cause produces an effect and every effect can, in principle, be traced back to its cause. The equations are elegantly simple. If you know the position and velocity of every particle in a system at a given moment, you can calculate exactly where those particles will be at any point in the future, and equally at any point in the past. The mathematics flows equally well in both directions. There is nothing in Newton's framework that says this moment is after that one. There is no arrow in the algebra. Move forward to the 19th century and the development of electromagnetism, and the same neutrality appears. James Clerk Maxwell wrote down his famous equations describing how electric and magnetic fields propagate through space. These equations predict the existence of electromagnetic waves, including light itself, and those equations too are time-symmetric. A light wave travelling forward through space follows the same mathematical rules as a light wave travelling backward. The physics of electromagnetism does not distinguish past from future. Go deeper still into the 20th century and the strange, counterintuitive world of quantum mechanics. The equation that governs how quantum systems evolve in time, the Schrödinger equation, is also time-symmetric. If you take a solution to the Schrödinger equation and run it in reverse, you get another valid solution. The mathematics of quantum states does not know which end of the timeline is which. Even Einstein's general theory of relativity, which completely reimagined the nature of space and time as a unified fabric that curves and bends in the presence of mass and energy, writes its equations in a form that is indifferent to the direction of time. The general relativistic equations that describe a black hole absorbing matter work just as well when you reverse them and watch the black hole spitting matter back out. Nature's rulebook, at the fundamental level, appears to have no arrow anywhere in it. And yet, here you are, growing older rather than younger. Here you are, remembering yesterday but not tomorrow. Here you are, watching the universe persistently and unfailingly move from order toward disorder, from the organized to the scattered, from the structured to the chaotic. There is an arrow. It is the most obvious feature of your daily existence, and physics cannot find where it comes from. The story of how scientists have tried to solve this problem begins in the Victorian era, with a bearded Austrian physicist named Ludwig Boltzmann, a man whose life and work were so deeply entangled with the mystery of time's arrow that the story of one cannot be told without the other. Boltzmann was born in Vienna in 1844, at a time when the Industrial Revolution was transforming European society, and the steam engine was becoming the defining technology of the age. It was the steam engine, and the science of how heat flows and work is done, that had given rise to thermodynamics. And it was thermodynamics that had produced the troubling law that sat at the centre of everything Boltzmann would spend his life trying to understand. The second law of thermodynamics had been articulated by Rudolf Clausius in the 1850s, and it stated something that every engineer who had ever built a steam engine knew intuitively to be true. In any closed system, the quantity called entropy tends to increase over time, or at the very least, it never decreases. Entropy was a measure of something difficult to define precisely, but easy to recognize in practice. A neat stack of papers has low entropy. The same papers scattered across a desk have higher entropy. An ice cube sitting in a warm glass of water has low entropy. After the ice melts and the temperatures equalize, the entropy is higher. The universe, Clausius was saying, relentlessly moves from low entropy to high entropy, from order toward disorder, from the organized toward the chaotic, and this process is irreversible. This was the arrow of time before anyone had called it that. The name would come later in 1927 from the British astrophysicist Arthur Eddington, who in his book The Nature of the Physical World gave the concept its now famous label and tied it explicitly to the one-way direction of entropy increase. Eddington was remarkably precise about what he meant. He said that the arrow of time is vividly recognized by consciousness, is insisted on by our reasoning faculty, and makes no appearance in physical science except in the study of the organization of many individuals, meaning entropy, a statistical phenomenon arising from large collections of particles. He described it as the most basic and irreducible feature of our experience of reality, and he argued that the same arrow would be recognized by any intelligent beings anywhere in the universe, that it was not a quirk of human psychology or biology, but a genuine feature of the cosmos itself. Eddington also identified a cosmological arrow, the direction in which the universe is expanding, which had been discovered by Edwin Hubble at roughly the same time Eddington was writing. The two arrows, thermodynamic and cosmological, appeared to point in the same direction, a fact that later researchers would recognize as deeply significant. But the puzzle itself was Clausius's, and it was Boltzmann who spent the most anguished and brilliant years of his life trying to figure out where the arrow came from. The problem that Boltzmann recognized was devastating in its simplicity. The second law says that entropy always increases, but the underlying physics, the collisions of gas molecules, the interactions of particles, all of that is time-symmetric. How can you derive a time-symmetric law from time-symmetric foundations? How can you get an arrow out of equations that carry no arrow of their own? Boltzmann's approach was statistical. He realized that entropy was not a property of individual particles, but of the vast statistical ensemble of all the possible ways particles could be arranged. A low-entropy state, like a gas where all the molecules are crowded into one corner of a container, corresponds to a very small number of possible microscopic arrangements. There are only so many ways to have all the gas in one corner. A high-entropy state, like the same gas spread uniformly throughout the container, corresponds to an astronomically larger number of possible arrangements. There are countless ways for the gas to be spread out, and only a handful of ways for it to be all in one corner. And this, Boltzmann argued, is why entropy increases. It is not a law imposed from outside. It is simply overwhelmingly probable. If you have a system in a low-entropy state, and you let it evolve randomly, according to the time-symmetric laws of physics, it will almost certainly move toward higher entropy, because there are so enormously many more high-entropy states than low-entropy ones. It is the same reason that if you shuffle a perfectly ordered deck of cards, you will almost certainly not produce another perfectly ordered deck. Not because shuffling is forbidden to produce order, but because disordered arrangements outnumber ordered ones by such a staggering margin that order is, in practice, unreachable by chance alone. This was a profound insight. Boltzmann had connected the abstract concept of entropy to a concrete physical reality, the number of microscopic configurations corresponding to a given macroscopic state. He had made thermodynamics statistical, probabilistic, and in doing so he had made it compatible, at least in spirit, with the reversible physics of individual molecules. Entropy increases because it is overwhelmingly probable that it will, not because it must. But then a colleague and mentor named Joseph Loschmidt pointed out a problem, a devastating problem, one that Boltzmann never fully escaped. If the underlying physics is reversible, Loschmidt argued in 1876, then for every trajectory of molecules moving from low entropy to high entropy, there is an exactly equally valid reverse trajectory moving from high entropy to low entropy. The equations permit both. If you took all the molecules in a gas at some moment and perfectly reversed all of their velocities, they would retrace their paths and return to the lower entropy state they started from. The mathematics guaranteed it. So Boltzmann's statistical argument proved too much. Yes, it predicted that entropy would increase going forward from any given moment, but it predicted equally well that entropy would have been increasing going backward from that moment too, which means entropy should be highest right now and lower in both directions of time. But that is not what we observe. We observe that entropy was lower in the past, not lower in both directions equally. This is Loschmidt's paradox, and it is sharper than it might first appear. It reveals that the statistical argument, if taken at face value, gives you the wrong answer about the past. If the present moment is statistically typical given the laws of physics, then the most probable history is one in which entropy fluctuated down to our current level from a higher state in both directions equally. But we do not live in a universe where the past was at high entropy. We live in a universe where the past was at lower entropy than the present. The Big Bang was at extraordinarily low entropy. The early universe was extraordinarily smooth and uniform. And that fact, that the past was special and unusually ordered, is not something that falls out of the laws of physics by themselves. It is something we have to add by hand as a boundary condition, an assumption about initial conditions that the equations themselves do not demand. This is what the philosopher of physics David Albert at Columbia University named the past hypothesis, and it is, in a very real sense, both the most compelling explanation for the arrow of time and the least satisfying one. It says, the universe started in an unusually low entropy state, and time's arrow is the universe's long, slow climb toward the statistical equilibrium it has been moving toward ever since the Big Bang. The arrow of time on this account is not a fundamental feature of the laws of physics. It is a consequence of initial conditions. We happen to live in a universe that started out highly ordered, and we observe the arrow of time because we happen to be living in the portion of that universe's history where it is still moving away from that extraordinarily ordered beginning. The Caltech cosmologist Sean Carroll, who has written and spoken extensively on this subject, puts it with characteristic clarity. Every difference between the past and the future, he says, is ultimately traceable to the fact that entropy is lower in one direction, the fact that we remember the past but not the future, the fact that we are born and then we live and then we die, always in that order, the fact that you can make an omelette from an egg but you cannot make an egg from an omelette. All of it, every manifestation of time's arrow in everyday experience, flows from the single fact that entropy was lower in the past. And the reason entropy was lower in the past, Carroll argues, is that the Big Bang created a universe in an exceptionally low entropy initial state. What we need to figure out, he says, is why the early universe had such low entropy to begin with. That question, why the Big Bang produced such an extraordinarily ordered cosmos, is the deeper mystery. It is the question behind the question, and it remains genuinely open. Here, before we go deeper into the cosmological implications, it is worth pausing to note something about the nature of these investigations. The ideas we are exploring come from peer-reviewed science, from careful work by professional physicists who have spent careers on these questions. But this is also a field where the fundamental debates are genuine and ongoing. As always, I would encourage you to seek out the original sources, to read the scientists themselves, to bring the same critical curiosity to these ideas that drives the researchers who study them. The richest understanding comes from engaging with multiple perspectives, rather than accepting any single account as the final word. With that said, let us push further into the territory that the past hypothesis opens up, because while it gives us a framework for thinking about time's arrow, it immediately raises a question that is more cosmological than physical. Why did the universe begin in such an extraordinarily low entropy state? This is where the work of Roger Penrose, the Nobel Prize-winning British mathematician and theoretical physicist, becomes essential. Penrose has argued, with considerable mathematical force, that the low entropy of the Big Bang is not just any puzzle, but one of the most extreme fine-tuning problems in all of cosmology. To appreciate Penrose's argument, you need a sense of scale. The current observable universe is about 93 billion light-years in diameter. It contains somewhere in the neighbourhood of 2 trillion galaxies, each containing hundreds of billions of stars. The total number of possible arrangements of all the matter and energy in this universe is almost incomprehensibly vast. Penrose worked through the mathematics and concluded that if you randomly chose an initial state for the universe from all possible initial states consistent with what we observe today, the probability of randomly landing on a state as ordered as the Big Bang is roughly 1 in 10 to the power of 10 to the power of 123. That number is not just large. It is so large that writing it out in standard notation would require more digits than there are particles in the observable universe. It is so large that the word improbable is hopelessly inadequate to describe it. What this means is that the Big Bang was not just slightly unusual, it was extraordinarily, almost inconceivably, specifically ordered. And Penrose argues this demands an explanation that goes beyond simply asserting it as a brute initial condition. His proposed explanation is called the Weyl curvature hypothesis. In general relativity, spacetime curvature is described by a mathematical object called the Riemann tensor, which can be decomposed into 2 parts. The Ricci tensor captures the curvature associated directly with the presence of matter and energy. The Weyl tensor captures the remaining tidal component of curvature, the gravitational field's intrinsic wrinkliness and distortion. Penrose proposed in 1979 that the initial Big Bang singularity was characterized by a Weyl tensor that was essentially zero. The gravitational field of the early universe was extraordinarily smooth, containing virtually no tidal distortions. And it is this initial smoothness of the gravitational field, Penrose argues, that is responsible for the low entropy of the Big Bang. A smooth, uniform gravitational field corresponds to a state of very low gravitational entropy, because there is only one way to be perfectly smooth and countless ways to be clumped and irregular. As the universe evolved and gravity pulled matter together to form stars, galaxies, and the enormous web of cosmic structure we observe today, the gravitational entropy increased. Black holes, which represent the maximum possible gravitational entropy for a given region of space, are in a sense the endpoint of this gravitational clumping process. The total entropy of the universe has been increasing ever since that smooth, Weyl tensor vanishing beginning, and the arrow of time is the direction of that increase. Penrose has extended this framework into a cosmological model called conformal cyclic cosmology, or CCC, in which the universe undergoes infinite cycles. Each cycle begins with a low entropy, Weyl tensor vanishing Big Bang, and ends in the far future when all matter has decayed or been consumed by black holes, and even the black holes have eventually evaporated through Hawking radiation, leaving only a cold, diffuse sea of photons and massless particles. In Penrose's model, this far future state, which appears to be a high entropy endpoint, is conformally equivalent to the smooth low entropy beginning of a new cycle. The conformal structure of the distant future maps onto the conformal structure of a new Big Bang, and the cosmos begins again. Penrose's CCC model is speculative and remains the subject of active debate, but it represents precisely the kind of serious, mathematically precise attempt to explain the low entropy of the Big Bang that the magnitude of the problem demands. And it illustrates a broader point about why the arrow of time ultimately requires a cosmological explanation. You cannot solve the problem at ordinary scales. You have to go to the origin of the universe, to the most extreme boundary conditions that physics ever encounters, to find the source of the asymmetry we experience every day. From a different direction entirely, Carroll and his collaborators have been pursuing an alternative approach. Rather than positing special initial conditions as a brute fact and then trying to explain them, Carroll has been attempting to build cosmological models in which low entropy initial states arise naturally, as typical outcomes of the dynamics rather than as imposed boundary conditions. In a 2004 paper with his then graduate student Jennifer Chen, Carroll explored the idea of a universe that does not have a maximum possible entropy, one where the entropy can grow without bound. In such a universe, any state is a low entropy state relative to what the universe could eventually become. Starting from any such state, the natural evolution is for entropy to increase in both temporal directions simultaneously, creating a past and a future that both look like higher entropy when viewed from the starting point. This approach tries to dissolve the past hypothesis rather than explain it. It says we should not think of our universe as starting at a special low entropy point from which time flows one way. We should think of it as a fluctuation in a vastly larger cosmos, one that naturally gives rise to regions where time flows in one direction for local observers. The arrow of time on this account is a local phenomenon, a consequence of the particular kind of statistical fluctuation that gave rise to our observable universe. Neither Carroll's approach nor Penrose's is universally accepted, and both face serious challenges. The debate between them represents some of the most sophisticated and carefully reasoned work currently being done on the foundations of physics. Now let us take a detour through a thought experiment that is almost 160 years old and that has never stopped generating new insights. In 1867, James Clerk Maxwell proposed an imaginary scenario that seemed to violate the second law of thermodynamics entirely. Imagine a container of gas divided in half by a wall. In the wall there is a tiny door, and next to the door sits a tiny intelligent being, later called Maxwell's demon. The demon watches the molecules of gas approaching the door. When a fast, hot molecule approaches from the right, the demon opens the door and lets it pass to the left side. When a slow, cold molecule approaches from the left, the demon opens the door and lets it pass to the right. Over time, the left side fills with hot molecules and the right side with cold molecules. The gas has been sorted into hot and cold halves without any apparent expenditure of energy. The entropy of the gas has decreased. The second law appears to have been violated. For nearly a century, physicists wrestled with this demon. Various proposed solutions were offered and found wanting. It was not until 1961 that a physicist at IBM named Rolf Landauer provided what is now generally accepted as the definitive resolution. Landauer's key insight was that the demon must measure and record information about each molecule it observes. It must remember which molecules are fast and which are slow, must maintain a record of its observations in order to decide when to open the door. This information has to be stored somewhere in whatever physical system constitutes the demon's memory. And information is physical. It is stored in physical states, and when those states are changed, energy and entropy are involved. Specifically, Landauer showed that the erasure of one bit of information, the act of resetting a memory element from a recorded state back to a blank state, always releases at least a minimum amount of heat into the environment. This minimum amount is given by Boltzmann's constant times the temperature times the natural logarithm of 2. The demon must periodically erase its memory to make room for new observations, and every erasure releases heat and increases entropy in the surrounding environment by at least the amount that the demon's sorting reduced it. The second law is saved not by forbidding the demon's clever sorting, but by charging an entropic price for the very act of acquiring and erasing information. Charles Bennett at IBM extended Landauer's work in the 1980s and showed how it fully resolves the Maxwell's demon paradox. What Landauer's principle establishes, and what has since been verified in experiments with increasing precision, is a deep, concrete connection between information and thermodynamics. Information is not abstract. The act of erasing information generates entropy just as surely as burning fuel or allowing a gas to expand. And this connection has consequences not just for thought experiments, but for the design of real computers, for quantum information theory, and for cosmology. Claude Shannon had anticipated part of this connection in 1948, when he showed that the information content of a message could be quantified using an equation that was mathematically identical to Boltzmann's formula for thermodynamic entropy. This was not a coincidence. Shannon entropy and Boltzmann entropy are, in a deep sense, the same thing. Both measure the number of possible states that a system or a message could occupy. A low entropy state is one about which we have a great deal of information, a highly constrained and specific arrangement. A high entropy state is one about which we have little information, a state that could be realized in an enormous number of ways. What this means is that entropy, and therefore the arrow of time, is fundamentally about information. The arrow of time is the direction in which information is irreversibly lost, the direction in which the detailed microscopic information about the initial state of the universe has been spreading and diluting through physical processes, becoming less accessible and less recoverable with every passing moment. Every computation that erases information increases the entropy of the universe. Every record that fades, every memory that dissolves, every calculation that is cleared from a register contributes to the inexorable entropy increase that defines time's arrow. The arrow of time is not something remote and cosmological. It is happening in every physical process, including the ones occurring right now in the machinery of your own mind. Now let us return to the question of whether the arrow of time has any fundamental origin in the laws of physics themselves, or whether it is, as the past hypothesis suggests, a purely contingent feature of initial conditions. Because there is one place in fundamental physics where the laws do carry a genuine, if small, preference for one direction of time, and discovering that place required some of the most subtle and precise experiments in the history of particle physics. In 1964, physicists studying the decay of particles called neutral kaons made a startling discovery. The neutral kaon, a subatomic particle containing a strange quark and an antiquark, was expected to behave identically whether time flowed forward or backward, a property called t-symmetry, or time reversal symmetry. Instead, experiments at Brookhaven National Laboratory revealed that the kaon's decay showed a slight but measurable violation of a combined symmetry called CP symmetry, where C stands for charge conjugation and P stands for parity. Since physics obeys a combined theorem called CPT symmetry, a violation of CP implies a violation of T. The laws governing kaon decay were not perfectly symmetric between past and future. In 2012, the Babar experiment at the Stanford Linear Accelerator Center provided a far more direct and dramatic demonstration of T violation, this time using neutral B mesons, heavier particles containing a bottom quark. The Babar collaboration exploited quantum entanglement to compare processes that were genuine, mathematical time reversals of each other, asking whether the rate at which a B meson transformed into its antiparticle matched the rate at which the antiparticle transformed back. The rates are different. The universe, at the level of weak nuclear interactions, genuinely treats forward time and backward time differently. The results were unambiguous, and the physics community acknowledged a landmark finding. T-symmetry is broken in nature. This is experimentally verified fact, not theoretical speculation. However, this T-violation in particle physics almost certainly does not explain the thermodynamic arrow of time we experience every day. The asymmetry in weak nuclear interactions is extremely small and extremely specific. It affects the decays of certain exotic particles under very particular conditions. It has essentially nothing to do with why broken glasses do not reassemble, or why your morning coffee cools instead of heats. The gap between the tiny T violation found in particle physics and the overwhelming arrow of time we live with every day is so enormous that most physicists do not believe one explains the other. The thermodynamic arrow is a cosmological phenomenon, rooted in the past hypothesis in the low-entropy initial conditions of the universe. The T violation in particle physics is a separate, smaller, and largely unrelated feature of the fundamental laws. Now let us consider something that Boltzmann himself found deeply troubling, an implication of his own statistical framework that has become one of the most important constraints on modern cosmological theories. It is called the Boltzmann brain problem, and it is as philosophically vertiginous as it sounds. Boltzmann, working in the late 19th century, was aware that his statistical mechanics predicted not just the probable increase of entropy, but also, as a necessary logical consequence, the eventual occurrence of improbable decreases. Given enough time, even an enormous statistical fluctuation, one that temporarily reduced entropy in a large region, was not forbidden by the mathematics. It was merely overwhelmingly unlikely. But in an infinitely old universe, even overwhelmingly unlikely events would eventually occur. Later researchers, developing this thread, arrived at a disturbing conclusion. In an infinitely old universe at or near thermal equilibrium, statistical fluctuations would occasionally produce configurations that happened to resemble a single human brain, complete with all its memories, perceptions, and sense of being embedded in a coherent history. Such a brain would have false memories of a past that never happened, would believe itself to be a real person in a real universe, and would almost immediately dissolve back into the thermal noise from which it had randomly arisen. These are Boltzmann brains. The problem is mathematical and quantitative. In an infinitely old universe at equilibrium, fluctuations the size of a single brain would be astronomically more common than fluctuations the size of an entire observable universe, which means that any given observer, statistically speaking, is overwhelmingly more likely to be a Boltzmann brain, a momentary random fluctuation with false memories, than a real person embedded in a genuine cosmic history emerging from a low-entropy Big Bang. Carroll has used this problem as a serious constraint on cosmological theories. Any theory that allows the universe to persist indefinitely in a state of high entropy, generating Boltzmann brains at random through statistical fluctuations, is making predictions inconsistent with our own existence as genuine observers embedded in real histories. This constraint rules out certain otherwise appealing cosmological scenarios and pushes theorists toward models with genuine, irreversible arrows of time rather than merely local, fluctuation-based ones. Ludwig Boltzmann himself never fully resolved these tensions, and his life was marked by struggles that went far beyond the intellectual. His atomistic view of matter, which was central to his statistical interpretation of entropy, was vigorously attacked by a school of physicists known as the energeticists, led by the influential chemist Wilhelm Ostwald, who maintained that atoms were merely convenient mathematical fictions rather than real physical entities. Ernst Mach, whose philosophy of science Boltzmann deeply disagreed with, was another prominent skeptic. These debates were not merely academic, they were battles over the foundations of physics, and Boltzmann found himself increasingly isolated as the century turned. He suffered from severe depression throughout his adult life, what we might today recognize as bipolar disorder, and the sustained intellectual hostility he faced appears to have intensified his suffering. In September 1906, while on vacation with his family in the Italian coastal village of Duino near Trieste, Boltzmann took his own life. He was 62 years old. The irony of his fate is one of the most poignant stories in the history of science. Just a few years after his death, experiments by Jean Perrin on Brownian motion provided the first conclusive experimental proof of the reality of atoms and confirmed the statistical mechanical framework Boltzmann had pioneered. The community that had often dismissed his ideas was vindicated, but he was not there to see it. His formula, the equation engraved on his tombstone in Vienna, S equals K times the natural logarithm of W, where S is entropy, K is Boltzmann's constant, and W is the number of microscopic configurations corresponding to a given macroscopic state, remains one of the most important equations in all of physics. It is the equation that connects the abstract macroscopic quantity of entropy to the concrete, microscopic reality of physical states. It is the equation that puts the arrow of time on a statistical probabilistic foundation, and its deepest implications are still being worked out more than a century after it was written down. Now let us look forward to where the arrow of time is taking the universe, because the story of the arrow is not just a story about how the universe began, it is also a story about where the universe is going. And that destination is one of the most extraordinary and vertiginous concepts in all of science. The second law tells us that entropy increases. The arrow of time points from lower entropy toward higher entropy, and if we follow that arrow forward to its ultimate conclusion, we arrive at what physicists call the heat death of the universe, a final state of maximum entropy from which no further change is possible. This concept, first articulated by William Thomson, later known as Lord Kelvin, in the 1850s and developed further by Clausius, describes a future so remote that describing it strains imagination. In the very far future of our universe, stars will exhaust their nuclear fuel and die. The last stars are expected to burn out in something like 100 trillion years, a timescale roughly 10,000 times the current age of the universe. After that, stellar remnants, white dwarfs, neutron stars and black holes will persist for far longer. White dwarfs will cool over timescales of perhaps 10 to the 37th power years, becoming cold, dark objects barely above absolute zero. Protons themselves may eventually decay, on timescales of at least 10 to the 40th power years, transforming the last atoms into radiation. The black holes will outlast all of this, but even they are not immortal. Stephen Hawking's theoretical work in 1974 showed that black holes slowly radiate away their mass through a quantum process now called Hawking radiation. Over timescales of roughly 10 to the 100th power years, a number written as a 1 followed by 100 zeros, the last black holes will evaporate completely, releasing their mass and energy as a diffuse sea of low-energy photons and elementary particles. After that, a universe at or near maximum entropy remains. Temperatures uniformly just above absolute zero. No stars, no planets, no structures, no gradients of energy to drive any further change. The cosmos will have reached the state that thermodynamics calls thermal equilibrium, sometimes called the heat death, a state in which nothing interesting can happen anymore because there are no more differences in temperature, energy, or entropy to drive any process. In such a universe, the arrow of time would effectively cease to have meaning. Without entropy differences, without the gradient from lower to higher disorder, there is no forward and no backward. Time would continue in the mathematical sense, but it would carry no arrow. It would be direction-free. This is the destination to which our universe appears to be heading, on a timescale so enormous that all of human history and all of the Earth's geological history would be a rounding error in the calculation. And in this destination, the full profundity of the arrow of time becomes clear. We live in a brief, luminous interval between an improbable beginning and a featureless end. The arrow of time is real and powerful precisely because we are alive in the middle of the journey, far enough from the low entropy beginning that entropy has had time to build complex structures like stars and planets and brains, but close enough to the beginning that enormous entropy gradients still exist, gradients that drive every process we recognize as life. This is the context in which to understand the arrow of time. It is not a permanent feature of the universe, it is a phase, a long phase, unimaginably long by human standards, but a phase nonetheless. The universe began in extraordinary order, and it is moving toward extraordinary disorder, and we exist in the gap between those two states, driven forward by the relentless, statistical, overwhelmingly probable tendency of entropy to increase. Boltzmann's statistical mechanics gives us the tools to understand this. Penrose's Weyl curvature hypothesis gives us a candidate explanation for why the beginning was so special. Carroll's work asks why the beginning existed at all, and what kind of cosmic framework might make such beginnings natural rather than miraculous. And the information-theoretic perspective developed by Shannon, Landau, and Bennett gives us a way to understand the arrow not just as a feature of gases and heat engines, but as a fundamental property of knowledge, memory, and the structure of rational experience itself. Ludwig Boltzmann died not knowing whether his atoms were real, not knowing whether the framework he had built would survive the century. But he understood, more clearly than almost anyone before or since, that the arrow of time was not a simple thing. He understood that it connected the largest scales of the cosmos to the smallest scales of molecular motion, that it connected abstract mathematics to the most vivid features of human experience. He understood that it could not be solved by clever derivations alone, that it required understanding something about why the universe is the way it is rather than some other way. He was right. More than 140 years after he began working on these questions, they remain open. The arrow of time is not just a problem in physics, it is the problem of how a universe governed by equations without a direction gave rise to a cosmos with a very definite one. And as we push forward into the frontiers of quantum gravity, quantum information theory, and cosmology, we are moving toward answers that will illuminate not just the nature of time, but the nature of everything. The equations are time-symmetric. The universe is not. And somewhere in the space between those two facts, the deepest truth about the cosmos is waiting to be found. And yet, for all the richness of what we have covered so far, we have barely scratched the surface of the territory that lies ahead. Because the arrow of time, as puzzling as it is in the language of classical thermodynamics, becomes even stranger, even more bewildering, when you carry it into the realm of quantum mechanics. And that is where physics has been pushing in recent decades, into a territory where time and entropy and quantum reality intertwine in ways that challenge even the most seasoned intuitions. To understand why quantum mechanics complicates the story, you need to appreciate what the Schrödinger equation actually tells us. This equation, formulated by Erwin Schrödinger in 1926, describes how the quantum state of a physical system evolves over time. The quantum state is represented by a mathematical object called the wave function, which encodes all the information about the possible configurations of the system and the probabilities of finding it in any particular one. The Schrödinger equation tells us how this wave function changes from moment to moment. And as we noted earlier, It does so in a way that is perfectly time-symmetric. Run the equation forward, and you get one valid evolution of the wave function. Run it backward, and you get another equally valid evolution. There is no arrow in the equation, but here is where quantum mechanics introduces a complication that has no parallel in classical physics. When you actually measure a quantum system, when you perform an observation or an experiment, something extraordinary happens. The wave function, which before measurement described a superposition of many possible outcomes with various probabilities, abruptly resolves into a single definite outcome. The superposition collapses, one possibility is selected, all the others vanish. And this process, called wave function collapse, is not described by the Schrödinger equation at all. It appears to be something different, something discontinuous, something that happens outside the smooth, reversible evolution that the equation governs. This measurement problem, as it is called, is one of the deepest unresolved issues in all of quantum theory. Different interpretations of quantum mechanics handle it in radically different ways. In the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, wave function collapse is a fundamental primitive feature of quantum theory. It happens when a quantum system interacts with a macroscopic measuring apparatus. It is irreversible. It is not described by any equation. It simply occurs. In the Copenhagen view, measurement introduces a genuine irreversibility into the quantum world. The many-worlds interpretation, proposed by Hugh Everett in 1957, takes the opposite approach. In this framework, there is no collapse at all. The Schrödinger equation always applies, everywhere, without exception. When a measurement occurs, the measuring apparatus becomes quantum mechanically entangled with the measured system, and the combined state evolves into a superposition containing all the possible outcomes, each in its own separate branch. From the perspective of any given branch, it looks as if collapse has occurred. But globally, nothing has collapsed. The entire universe continues to evolve reversibly. In the many-worlds interpretation, there is no independent arrow from quantum measurement. There is only the same thermodynamic arrow we have been discussing all along, arising from the same entropic considerations, the same past hypothesis, the same low-entropy initial conditions. What looks like the irreversibility of measurement is just the ordinary irreversibility of thermodynamic processes playing out at the quantum scale. And here the concept of quantum decoherence becomes crucial. Decoherence is the process by which a quantum system, through interaction with its environment, loses its quantum superposition and begins to behave classically. When quantum information about a superposition spreads outward into the environment, becoming entangled with an enormous number of degrees of freedom, the superposition does not vanish, but it becomes effectively inaccessible. Tracking it would require monitoring the quantum state of the entire environment, which is practically impossible. Decoherence is what makes the quantum world look classical at the scales we observe, and crucially for our story, decoherence is a thermodynamic process. It increases entropy. When quantum information spreads into the environment, the total entropy of the system plus environment increases, just as in any ordinary thermodynamic process. The arrow of decoherence, the direction in which quantum systems lose their coherence and become classical, is the same as the thermodynamic arrow of time. And that means decoherence, for all its quantum novelty, traces back to the same source as everything else, the low-entropy initial conditions of the Big Bang. This convergence is one of the most striking features of modern physics. The way that quantum measurement, thermodynamic entropy, information erasure, and cosmological initial conditions all point back to the same ultimate source suggests that the arrow of time is not a coincidental alignment of separate phenomena, but a single, deeply unified feature of the universe, manifesting in different languages in different contexts but always, at root, arising from the same statistical asymmetry between the improbable beginning and the probable end. Now let us consider what the arrow of time means not just for the large structures of the cosmos, but for the intimate personal fact of human existence. A memory is a physical record of a past event, a pattern in the neural structure of your brain that was caused by something that happened and that persists because it requires an extraordinarily improbable thermodynamic reversal to erase. Memories are asymmetric in time because records form in the direction of increasing entropy and dissolve only with enormous improbability. Your memories of childhood, of yesterday, of this morning, all exist because thermodynamic processes ran in one direction, leaving traces that persist. Causality, the principle that causes precede effects, is tied to the arrow of time in exactly the same way. We define causation in terms of the temporal sequence of events in the entropy increasing direction. If the arrow pointed the other way, our intuitions about cause and effect would be exactly reversed. Eddington appreciated this when he coined the term arrow of time in 1927. The arrow, he said, is the foundation of rational thought itself. Every argument, every inference, every form of reasoning that proceeds from evidence to conclusion presupposes the arrow of time. Take away the arrow, and the entire structure of rational thought collapses. There is something extraordinary about this realization. The universe began in an extraordinarily improbable, highly ordered state about 13.8 billion years ago. The second law of thermodynamics has been driving entropy upward ever since. And from that simple, cosmic statistical fact has emerged everything we experience: memory, causality, rational thought, the sense of moving through time, the ability to plan and to know and to understand. The arrow of time is not just a problem in physics, it is the precondition of our existence as thinking beings. For all that we have learned, the deepest question remains open. Why did the universe begin in that extraordinarily low entropy state? What mechanism or principle could make such a beginning natural rather than miraculous? These questions point toward physics that does not yet exist, toward a theory that unifies quantum mechanics and general relativity, a theory of quantum gravity that might explain not just the arrow of time, but the origin of time itself. In the next part of this journey, we will follow these ideas to their frontier. We will examine the remarkable proposal that time itself might be emergent, that at the deepest level of physical reality there may be no time at all, and that what we experience as the flow of time arises from quantum entanglement and the growth of information correlations in a fundamentally timeless structure. We will look at recent work in quantum information theory that has shed new light on the arrow of time at the quantum scale. We will examine the extraordinary debate over whether information is destroyed when matter falls into a black hole, a debate that has engaged the most brilliant minds in theoretical physics for decades, and that may, when finally resolved, reveal something fundamental about the nature of time itself, and we will follow the thread of the arrow of time all the way to the frontier of cosmology. The equations have no arrow, the universe has one, and the story of how the second of those facts might follow from the first, when properly and deeply understood, turns out to be one of the most astonishing and beautiful stories in all of science. Before we depart this first chapter of our investigation, let us dwell on something that every treatment of the arrow of time eventually confronts, a paradox that sits at the very edge of what physics can say and what philosophy must take over. We have established that the arrow of time, in its most defensible physical form, is a consequence of initial conditions. The Big Bang was extraordinarily ordered. Entropy has been increasing ever since. The arrow points forward because the beginning was special. But now ask the following question. What does it mean to say the beginning was special? Special compared to what? Special compared to all the other possible initial states, the countless configurations the universe could have started in but did not. And how do we access or even conceive of those other possible initial states? They never happened. They do not exist, at least not in our universe. We are comparing our actual universe to an ensemble of hypothetical universes that have no physical reality. Is that a legitimate scientific argument? This is not a frivolous philosophical quibble. It goes to the heart of what the past hypothesis actually explains. When Penrose says that the probability of the Big Bang initial state is 1 in 10 to the 10 to the 123, that probability is calculated with respect to a particular measure, a particular way of counting possible states. But there is no unique, physical, obviously correct measure. Different choices of measure give different probabilities, and the choice of measure is, in a sense, already smuggling in assumptions about what counts as typical or special. The argument becomes circular in a subtle way. We are using the very framework that produces the arrow of time to argue that the low entropy initial state is improbable, but the framework already assumes a notion of probability that depends on the arrow of time. Carroll and Albert have both written carefully about this circularity, and they agree that it is real but not necessarily fatal. The past hypothesis can still do explanatory work, even if we cannot derive it from more fundamental principles. It constrains the initial state and, combined with the time-symmetric laws, correctly predicts everything we observe about the direction of time, the existence of records, the reliability of thermodynamics, and the structure of causal reasoning. It is not a derivation from first principles, but it is a genuine scientific hypothesis, one that makes predictions and that could in principle be falsified if we discovered evidence of a universe in which entropy had been higher in the past. That we have found no such evidence, that every observation is consistent with a universe that started in a low entropy state and has been increasing entropy ever since, is genuine support for the hypothesis, even if it is not a proof. There is also a deeper, more philosophical dimension to the puzzle, one that Carroll has explored in his book From Eternity to Here. It concerns the question of whether time itself had a beginning, whether the Big Bang was genuinely the first moment of the universe, or whether something existed before it in some meaningful sense. Standard cosmology treats the Big Bang as the initial singularity, the moment at which the universe's evolution began. But quantum gravity, which we do not yet have a complete theory of, might change this picture. Some approaches to quantum gravity suggest that the concept of time itself breaks down at the Planck scale, the scale at which quantum effects of gravity become important. Others suggest that the universe might be eternal in some sense, with the Big Bang being a transition from a previous phase rather than an absolute beginning. If the universe is eternal, then the question of why the Big Bang had low entropy becomes even more pressing. Why, in an eternal universe, did this particular moment have such extraordinarily low entropy? Why not some other moment? And if the universe is not eternal, if the Big Bang truly was the beginning, then we must ask what determined the initial conditions, what set the entropy so low at the start, and whether that question even has a physical answer, or whether it lies permanently beyond the reach of science. These are not rhetorical questions. They are active research problems, pursued by serious physicists and philosophers of physics at institutions around the world. The answers, when they come, will not come from thought alone. They will require new mathematics, new theories, and potentially new experimental evidence of a kind we cannot yet fully specify. What we can say, standing at the edge of our current knowledge, is this. The arrow of time is one of the most profound and productive mysteries in all of science. It has driven the development of statistical mechanics, thermodynamics, quantum decoherence, quantum information theory, and the foundations of cosmology. It has forced physicists to think carefully about what it means for a law to be fundamental, what it means for an initial condition to be special, and what it means for time itself to have a direction. It has connected the smallest scales of physics to the largest, the most abstract mathematical structures to the most concrete features of everyday experience. And it remains open, not in the sense that we have no ideas, but in the most productive sense. We have good ideas, partial answers, deep insights, and we know enough to know that the full answer, when it arrives, will be something genuinely new, something that changes how we understand not just time, but the entire structure of physical reality. The glass falls, and it breaks. The equations say it could do otherwise. The universe says it will not. And in the space between those two statements lies one of the most beautiful and demanding questions that human minds have ever turned their attention toward. Yet even after acknowledging all of this, there are researchers who feel that the standard entropy-based account, compelling as it is, leaves something important unsaid. The complaint is not that the account is wrong, but that it is incomplete in a specific way. It explains why, given a low entropy beginning, time flows forward. But it does not explain what it is for time to flow at all. It does not explain why there is a subjective sense of the present moment, a sense of being here, now, moving through time. The equations of physics, including the equations of statistical mechanics, describe a four-dimensional block of spacetime in which every moment exists with equal ontological status. There is no privilege now in the mathematics. There is no moving spotlight of the present, yet we experience a present. We experience becoming. We experience time flowing. This is what philosophers call the problem of the flow of time, and it is distinct from the problem of the arrow. The arrow asks why past and future are different. The flow asks why there is a sense of movement from past to future, why the present feels vivid in a way the past and future do not. Some physicists, like Julian Barber, have argued that this apparent flow is an illusion, a cognitive construction that arises from the way minds process information, and that the block universe picture of physics is the true and complete picture of reality. Others argue that the block universe picture is itself an incomplete description, that it captures the relational structure of events but misses something about the dynamic, processual nature of becoming. The philosopher of physics Lee Smolin has argued persistently and provocatively that time is not just a useful parameter in physics, but a fundamental and irreducible feature of reality, that the future is genuinely open in a way the past is not, and that building this genuine openness into our physical theories requires a radical rethinking of what we mean by physical law. Smolin argues that the laws of physics themselves may evolve over time, that the constants and symmetries of nature are not fixed once and for all, but are shaped by the history of the universe, and that this evolutionary picture of physical law might provide a more fundamental source of temporal asymmetry than anything that emerges from statistical mechanics or initial conditions. These are minority views in the physics community. Most physicists are comfortable with the block universe picture and with the statistical account of the arrow. But minority views have a history of eventually becoming mainstream when they capture something that the prevailing consensus was missing. And there is a persistent sense, among some of the most careful thinkers on these questions, that the standard account, while almost certainly correct as far as it goes, does not yet go all the way. That sense of incompleteness is itself one of the most important features of the current state of knowledge about the arrow of time. It is the sense that drives the research. It is the sense that makes the problem productive rather than sterile. We have a good account, perhaps even a mostly correct one, and yet we can feel that the deepest level is still out of reach. Boltzmann felt something similar in the 1890s. He had the right framework, the right equations, the right statistical intuition, and yet he could feel that something about the problem was escaping him. He was right. The low entropy past, the initial conditions, the cosmological dimension of the puzzle, these were all things he sensed were essential but could not fully articulate. We are in an analogous position today. We have the right framework for the thermodynamic and statistical dimensions of the arrow. We understand the connection to quantum mechanics, to decoherence, to information theory. We have serious, mathematically precise proposals for explaining the low-entropy initial conditions through Penrose's Weyl curvature hypothesis, or Carroll's eternal cosmological models. We have the experimental evidence from particle physics confirming T-violation in weak interactions. We understand why memories form, why causality seems directed, why the psychological and thermodynamic arrows align. And yet the deepest question remains: why did the universe begin in a low-entropy state? What, if anything, is time in the most fundamental sense? And is the arrow of time a permanent, eternal feature of reality? Or is it a temporary condition that will dissolve when the universe finally reaches the thermal equilibrium that the second law insists on? When the last black hole evaporates and the last photon cools to the temperature of the dark, will there still be a direction to time? Or will the concept itself, so fundamental to every human experience and every form of reasoning, finally and irreversibly dissolve? These questions are not merely academic. They point toward the deepest possible understanding of the nature of time, of existence, and of the remarkable, improbable, fleeting order that makes everything we know and love and think possible. We live in the brief, bright interval between the extraordinary beginning and the featureless end. We exist because of the arrow. We think because of the arrow. And we are, perhaps, the only entities in the known universe capable of wondering about it. That is where we stand at the close of this first chapter of our exploration. We have traced the arrow of time from its thermodynamic origins in the work of Clausius and Boltzmann, through the statistical and probabilistic framework that Boltzmann built and Loschmidt challenged, to the past hypothesis and its cosmological implications, to the particle physics experiments that found genuine T-violation in the weak nuclear force, to the information-theoretic connections established by Shannon and Landauer, to the quantum mechanical dimensions of the problem that involve decoherence and the measurement problem, to the ultimate fate of the universe in heat-death, and the question of what happens to the arrow when entropy reaches its maximum. We have encountered some of the most brilliant and passionate minds in the history of science, from a Victorian physicist who died for his ideas, to Nobel laureates who have spent careers refining the understanding of where time's direction comes from. And we have arrived at a set of open questions that are as rich and demanding as any in science. The journey is far from over. The strangest thing about the arrow of time is not that it exists. The strangest thing is what we discover when we try to locate it. Every time we push into the microscopic realm looking for the mechanism that forces time to flow forward, the mechanism dissolves. The atoms do not know which direction is forward. The The quantum fields do not know. Even the equations of quantum gravity, the deepest descriptions of physical reality that humanity has yet produced, appear to carry no arrow. And yet here, in the enormous complexity of the world we can see and touch and remember, the arrow is everywhere and inescapable. This is the territory we enter in the second part of our journey. We have established the classical and thermodynamic foundations of the arrow, traced it back to the extraordinary initial conditions of the Big Bang, and seen how it permeates even the structure of memory and rational thought. Now we push further into the frontiers of quantum mechanics, quantum gravity, black hole physics, and the astonishing possibility that time itself, as a fundamental concept, may not exist at the deepest level of nature. To begin this part of the story, we need to descend into the basement of physics, to a place where the familiar concept of time becomes genuinely problematic. Not just philosophically uncertain, not just difficult to measure, but absent. Mathematically absent. In the 1960s, two physicists named John Archibald Wheeler and Bryce DeWitt attempted to write down the quantum mechanical wave equation for the entire universe. The project arose from the effort to reconcile general relativity with quantum mechanics, the two great theories of the 20th century that together describe essentially all of known physics, and yet are profoundly, almost violently incompatible with each other. In ordinary quantum mechanics, time is a background parameter, the stage on which quantum events unfold. In general relativity, time is part of the dynamical fabric of space-time, something that curves and bends and is shaped by the presence of matter and energy. There is no obvious way to combine a theory in which time is fixed and external with a theory in which time is flexible and physical. This is called the problem of time in quantum gravity, and it has no universally accepted solution. Wheeler and DeWitt wrote down an equation that attempted to describe the quantum state of the entire universe, encoding both the geometry of spacetime and the matter fields within it in a single mathematical object called the wave function of the universe. The equation they derived, now called the Wheeler-DeWitt equation, has a feature that is simultaneously fascinating and deeply disturbing. It contains no time variable. The equation is frozen. The wave function it describes does not evolve. From the perspective of the Wheeler-DeWitt equation, the universe is a static, timeless structure. Everything that has ever happened and will ever happen is encoded in a single, unchanging quantum state. This is one of the most extraordinary results in all of theoretical physics. The equation that is supposed to describe the quantum universe does not contain time. If you take this equation at face value, then there is no such thing as temporal evolution at the most fundamental level of reality. The block universe that general relativity implies, where all moments of time exist simultaneously with equal reality, becomes, in this quantum gravitational context, not just a philosophical interpretation, but a mathematical necessity. The universe, at the level of quantum gravity, is timeless. But then how does time emerge? How does the experience of temporal flow, of one moment succeeding another, arise from a fundamentally timeless substrate? This is where the ideas of two physicists, Don Page and William Wouters, become important. In 1983, Page and Wouters proposed a mechanism by which time could emerge from the timeless quantum state of the universe through the phenomenon of quantum entanglement. The basic idea is elegant and counterintuitive. Imagine the universe divided into two parts. One part that acts as a clock and everything else. The clock is a physical system that has many possible states, each corresponding to a different reading. The rest of the universe, the system we want to observe evolving, is entangled with the clock. The total quantum state of the universe is frozen and timeless. But within that frozen state, the state of the system is correlated with the state of the clock. When we condition on the clock reading a particular value, we find the rest of the universe in a particular corresponding state. When the clock reads a different value, the rest of the universe is in a different state. Time, in this picture, is not a background parameter or an independent dimension. It is a relationship. It is the pattern of correlations between subsystems in a fundamentally timeless quantum state. What an observer inside the universe experiences as the flow of time is, on this account, the unfolding of these correlations. As the observer interacts with the clock, as the quantum state of the observer becomes entangled with the quantum state of the clock, the observer accumulates a sequence of correlated states that constitute a temporal experience. Time flows for the observer from the inside, even though the universe as a whole from the outside is perfectly static. This is a startling idea. It says that the flow of time, the most immediate and undeniable feature of our experience, is not built into the fundamental architecture of nature. It emerges from entanglement. It is a relationship, not a substance. It exists for internal observers, but not for an imagined external observer looking at the universe from outside. For decades, Page and Wouter's idea was treated as an interesting but unverifiable philosophical speculation. That changed in 2013 when a team of experimental physicists in Turin, Italy, led by Ekaterina Moreva and her colleagues, performed a groundbreaking experiment to test the mechanism directly. They created a tiny quantum system consisting of entangled photons, with one photon playing the role of the clock and the other playing the role of the rest of the universe. From the perspective of an external observer measuring both photons, the total quantum state appeared static with no evolution. But when an observer was simulated inside the system, tracking correlations between the clock photon and the system photon, time appeared to flow. The experiment confirmed, for the first time in a laboratory setting, that time is an emergent phenomenon for internal observers of a quantum system, but is absent for external observers. The predictions of the Wheeler-DeWitt equation and the Page-Wouter's mechanism were borne out. This result, published in Physical Review A, is one of the most philosophically significant experimental findings in recent physics. It suggests that what we call time, the thing we feel most immediately and viscerally in every moment of our lives, is not a fundamental ingredient of the universe. It is something that emerges from the quantum structure of correlations between physical systems. And if time is emergent, then the arrow of time is also emergent. It is not written into the most fundamental equations. It arises in the process of emergence itself. How precisely does the arrow arise in that process? This is where entropy and entanglement come together in a way that sheds new light on the old puzzle. In the Page-Wouter's framework, the state of the universe is initially a state of low entanglement between the clock and the rest of the system. As the correlations build up, as the entanglement between subsystems grows, what an observer inside the system experiences as the forward direction of time is precisely the direction in which entanglement is increasing. The arrow of time, on this account, is the direction in which quantum entanglement grows. It is the direction in which correlations spread, in which information about the initial state diffuses outward into the degrees of freedom of the environment. This is, at a deep level, the same thing as the increase of entropy, but expressed in the language of quantum information theory rather than classical thermodynamics. This convergence between the quantum information picture and the thermodynamic picture is one of the most exciting developments in recent foundational physics. It suggests that the two great traditions of thinking about time's arrow, the thermodynamic tradition that goes back to Boltzmann and the quantum informational tradition that has developed more recently, are not two separate explanations but two aspects of the same underlying reality. The arrow of time is the direction in which quantum correlations grow. Entropy is a measure of how much those correlations have spread, and the low entropy past is the direction in which those correlations had not yet fully developed, the direction of initial separability, of the unfurling that has been going on since the Big Bang. At this point in our exploration, it is worth taking a moment to reflect on how remarkable the current scientific picture actually is. We began with a simple, everyday observation. Things change in only one direction. Glasses fall and break. Coffee cools. People age. And we have traced that observation through statistical mechanics, cosmology, quantum mechanics, and quantum gravity to arrive at a picture in which the arrow of time is intimately connected to the nature of entanglement, to the origin of the universe, to the structure of space-time itself, and to the deepest questions about whether time is a fundamental or an emergent feature of reality. As always in the best science, a simple question has opened into something vast and intricate and beautiful. I want to pause here to emphasize something important. The ideas we are discussing in this second part of our journey are genuinely at the frontier of current understanding. They are not settled science in the way that, say, the second law of thermodynamics is settled. The Page-Wouter's mechanism is a fascinating and experimentally supported framework, but it is not the accepted consensus picture of quantum gravity, because we do not yet have a consensus picture of quantum gravity. The Wheeler-DeWitt equation is an important result, but it is part of a framework, semi-classical quantum gravity, that physicists know is incomplete. The connections between entanglement, entropy, and space-time that we are exploring are active research topics, not finished theorems. As a careful thinker, you should hold these ideas with appropriate uncertainty, following the ongoing research with curiosity and without premature commitment to any particular account. What makes these ideas compelling is not that they are proven, but that they are pointing in what many physicists feel is a genuinely productive direction. With that said, let us follow that direction into some of the most extraordinary physics of the past 3 decades, the physics of black holes, information, and the structure of space-time. No entity in the known universe has a more complex and revealing relationship with the arrow of time than a black hole. A black hole forms when enough matter collapses under its own gravitational weight into a region so dense that the curvature of space-time becomes extreme. The boundary of that region, the surface of no return beyond which not even light can escape, is called the event horizon. Everything that falls past the event horizon is, according to classical general relativity, gone forever. It adds to the black hole's mass but disappears from the universe of external observers. The black hole has only 3 properties visible from the outside: mass, electric charge, and angular momentum. This is the famous no-hair theorem. All other information about what fell in is erased. Stephen Hawking's discovery in 1974 that black holes are not entirely black, that they slowly radiate energy through a quantum process now called Hawking radiation, transformed the physics of black holes and the arrow of time simultaneously. Hawking showed that quantum effects near the event horizon cause pairs of virtual particles to be produced, one of which falls into the black hole and one of which escapes as radiation. Over time, this radiation carries away the black hole's mass, and the black hole shrinks. Over an enormous timescale, roughly 10 to the 100th power years for a black hole of stellar mass, the black hole evaporates completely. This is beautiful and important. But it leads to a paradox that Hawking himself recognized in 1976, one that has been the focus of intense theoretical debate ever since. The radiation that Hawking calculated is thermal. It is like the radiation from a hot body in thermal equilibrium. It carries no information about what fell into the black hole. It is, in a precise quantum mechanical sense, a completely mixed state, the quantum equivalent of maximum entropy. But quantum mechanics demands unitarity. The evolution of a quantum state must be governed by unitary operations, which preserve the total information content of the state. A pure quantum state, one that carries complete information, must evolve into another pure quantum state. Information cannot be destroyed. If a quantum system in a pure state, encoding detailed information about its structure, falls into a black hole, and the black hole eventually evaporates into featureless thermal radiation, then information has been destroyed. A pure state has evolved into a mixed state. Unitarity has been violated. This is the black hole information paradox. It sets 2 bedrock principles of physics directly against each other. General relativity and the no-hair theorem say information falls into the black hole and cannot escape. Quantum mechanics says information cannot be destroyed. One of them must be wrong, or at least incomplete. And the resolution of this paradox, which has not yet been fully achieved, will almost certainly require new physics at the frontier of quantum gravity. Hawking originally argued that information genuinely is destroyed, and that this destruction is the price we pay for having black holes in a quantum universe. He argued that the paradox should be resolved by accepting that quantum mechanics, in the context of gravity, does not preserve information, that black hole evaporation is a genuinely irreversible process at the fundamental level. This would mean that the arrow of time has a more fundamental source than statistics and initial conditions. It would mean that at the level of quantum gravity, in the extreme environment of a black hole, time genuinely is one-directional in a way that the ordinary time-symmetric equations of physics are not. Most physicists, however, became deeply uncomfortable with this resolution. The destruction of information would violate not just unitarity, but the predictability on which all of science depends. If information can disappear from the universe, then the past does not fully determine the present, and the entire framework of physical law is undermined. The search for an alternative resolution became one of the central problems of theoretical physics. In the 1990s and 2000s, 3 converging lines of research began to suggest a resolution. The first was the holographic principle, developed by Gerard 't Hooft and Leonard Susskind, which proposed that all the information in a region of space is encoded on its boundary surface, not in its interior. Applied to a black hole, This suggests that the information falling into the black hole is somehow encoded in the structure of the event horizon and eventually escapes, encoded in subtle correlations in the Hawking radiation. The radiation is thermal when you look at individual particles, but the totality of the radiation carries the information in delicate quantum correlations that are extremely difficult to detect but are there. The second was Juan Maldacena's extraordinary discovery in 1997 of what is now called the ADS/CFT correspondence, or more broadly the holographic duality. Maldacena showed that a theory of quantum gravity in a particular kind of curved spacetime, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime. The two theories, one with gravity and one without, describe exactly the same physics in different mathematical languages. This duality is unitary on the boundary side, which means, if the correspondence holds, it must also be unitary on the gravity side. Information is not lost. The black hole information paradox in this framework does not exist. The paradox is an artifact of trying to describe a quantum gravitational system using only the tools of classical gravity without properly accounting for the quantum nature of the spacetime. The third line of research was the work of Don Page, who showed in 1993 that if information is preserved and unitarity holds, then the entanglement entropy of the Hawking radiation must follow a specific curve, now called the Page curve. The entanglement entropy should rise as the black hole evaporates and then fall back to zero when evaporation is complete, tracing out a characteristic arc rather than rising monotonically. Recent work by researchers including Ahmed Almairi, Netta Engelhardt, Henry Maxfield, and Jeff Pennington, published between 2019 and 2020, provided a calculation using insights from holographic duality and a concept called quantum extremal surfaces that reproduces the Page curve. This is widely seen as strong evidence that information is indeed preserved during black hole evaporation, that the resolution of the paradox involves unitarity being maintained in a subtle way that only becomes apparent when quantum gravity effects are properly accounted for. What does all of this have to do with the arrow of time? The connection is profound. If information is not destroyed in black hole evaporation, then black holes do not introduce a genuinely new, fundamental source of temporal asymmetry. The arrow of time in black hole physics is still, at root, statistical and cosmological, arising from the same entropic considerations we have been discussing all along. But the resolution of the information paradox requires understanding how information is encoded in the Hawking radiation and how it escapes from the black hole, and answering these questions requires understanding the quantum structure of spacetime in ways that go far beyond anything in existing theories. One of the most provocative ideas to emerge from this research is the ER equals EPR conjecture, proposed by Maldacena and Susskind in 2013. ER stands for Einstein-Rosen, the term for a wormhole, a tunnel connecting two distant regions of spacetime. EPR stands for Einstein-Podolsky-Rosen, the term for quantum entanglement, the spooky correlation between distant quantum particles. The ER equals EPR conjecture proposes that these two apparently very different phenomena are in fact the same thing described in different languages. Two quantum particles that are entangled are, in a deep sense, connected by a microscopic wormhole. The quantum entanglement between the particles is the wormhole. This idea that entanglement is the fundamental glue that builds spacetime, that the connectivity of space is itself a manifestation of quantum correlations, has been developed by Mark van Ramsdonk and others into a picture in which spacetime emerges from entanglement. Reduce the entanglement between two regions, van Ramsdonk showed, and spacetime tears. Increase the entanglement, and spacetime weaves itself together. In this picture, the geometric structure of the universe, the fabric of spacetime that general relativity describes, is a derivative concept, something that appears when you coarse-grain over the quantum information of the underlying quantum state. Spacetime is emergent, and if spacetime is emergent, then time, as a feature of spacetime, is also emergent. The implications for the arrow of time are still being worked out, but the general direction is clear. If spacetime is woven from quantum entanglement, then the arrow of time, the direction in which entanglement grows and spreads, is the direction in which spacetime itself is being constructed. The forward direction of time is the direction in which the quantum correlations that build spacetime are increasing, the direction in which the holographic encoding of information on boundaries is becoming more complex. The arrow is not a feature of the fundamental timeless quantum state. It is a feature of the process of emergence, of the way the space-time we inhabit is being continuously built from quantum information. This is a deeply speculative picture, and its proponents would be the first to acknowledge that many steps remain to be taken before it can be called a complete or fully verified theory. But it represents the cutting edge of current thinking about time, and it illustrates how the question of the arrow of time has driven physics towards some of its most ambitious and creative theoretical ventures. Let us now turn to a striking series of experiments that brought the arrow of time into the laboratory in a way that challenged intuitions even further. In 2019, a team of physicists led by Gordy Lesovic at the Moscow Institute of Physics and Technology, working in collaboration with the Argonne National Laboratory in the United States, performed an experiment on an IBM quantum computer that generated headlines around the world. The experiment appeared to reverse the arrow of time. To understand what they actually did and what it means requires some care. The experiment worked with a tiny quantum system of 2 and 3 qubits, the basic units of quantum information. They initialized the qubits in a simple, localized quantum state, representing a particle in a relatively ordered configuration. Then they allowed the system to evolve forward according to the laws of quantum mechanics. The quantum state spread out, became more entangled with the environment, and evolved toward what looks like a more complex, less ordered configuration. This is the quantum analog of entropy increase, the forward direction of the arrow. Then the experimenters applied a specially designed quantum algorithm that effectively reversed the evolution, nudging the quantum state back toward its initial configuration. The key mathematical step was the application of a complex conjugation operation to the wave function, the quantum operation that is equivalent to time reversal. The system moved backward through its quantum evolution and returned to something close to its initial state. But here is the critical point, the one that the headlines often missed. This reversal was not spontaneous. It required the application of a carefully designed, externally controlled quantum algorithm. The experimenters had to intervene, had to do work, had to apply a specific sequence of quantum operations that required precise knowledge of the system's state and its evolution. The reversal was designed, artificial, and highly controlled. It did not happen on its own. In nature, without external intervention, the complex conjugation needed for time reversal would require the simultaneous, perfectly coordinated reversal of an exponentially large number of quantum states, a process so astronomically improbable that it would essentially never happen spontaneously. What the experiment demonstrated was not that nature can spontaneously reverse its arrow of time, but that, in a carefully controlled quantum system with only a few degrees of freedom, a designed algorithm can execute a time reversal. The probability of such a reversal occurring spontaneously in a macroscopic system, the researchers calculated, is roughly 1 in 10 to the power of 10 to the power of 16, a number so fantastically small that even in the entire history of the universe it would not occur for a glass of water, let alone for anything more complex. This is precisely what Loschmidt and Boltzmann argued about a century and a half ago. Time reversal is not forbidden by the laws of physics. It is merely overwhelmingly improbable for any macroscopic system. The IBM experiment made this abstract principle concrete and experimentally tangible, and it also pointed toward a new question. Could quantum computers, with their ability to execute precise quantum operations on carefully controlled quantum states, be used to probe the foundations of the arrow of time in ways that were previously inaccessible to experiment? The answer appears to be yes, and this represents one of the most exciting intersections of quantum technology with fundamental physics. As quantum computers become more powerful, capable of managing larger and more complex quantum systems, they will become tools for testing the limits of the arrow of time in controlled quantum environments, for exploring what happens to the arrow when entanglement is precisely managed, and for probing the transition between the quantum regime where time reversal is possible in principle and the classical regime where it is forbidden in practice. This is genuinely new experimental territory, and the results of the coming decade will likely contribute substantially to our understanding of the arrow of time. There is another dimension to the arrow of time that we have not yet fully explored, and it concerns not the direction of time's arrow but the nature of time itself. All of the accounts we have discussed so far treat time as something that exists, that flows, that has a direction. But there is a significant and respectable tradition in physics, associated particularly with the philosophy of the block universe, that questions whether time flows at all. In Einstein's special and general relativity, time is a dimension of space-time. It is spread out, coexisting with spatial dimensions in a four-dimensional block. Every event in the history of the universe occupies a definite location in this four-dimensional block, and every event is equally real regardless of whether it is in the past, present, or future of any given observer. There is no privileged now. There is no moving spotlight of the present. The sensation of time flowing, of the present moment advancing from past to future, is, in the block universe picture, not a feature of space-time but a feature of consciousness, or of how we process information. Julian Barbour, the British physicist who has spent decades working on the foundations of time in quantum gravity, has pushed this idea to its logical extreme. In his book The End of Time, published in 1999, Barbour argued that time does not exist at all, not even in the attenuated sense of a dimension of space-time. He proposed that the universe is better described not as a block of space-time but as a static configuration space, which he calls Platonia, in which every possible arrangement of the universe's matter fields exists with some probability amplitude, but no arrangement is inherently earlier or later than any other. What we experience as the passage of time is, in Barbour's picture, an illusion created by the structure of our memories and perceptions within a single, instantaneous configuration. Barbour's view is radical, to say the least, and most physicists do not adopt it as a working framework. But it forces a productive question. How do we know time flows? We infer the flow of time from memories of the past. But Barbour points out that memories are just a feature of the present configuration of our brains. They do not require that there was actually a past. A configuration could contain records of events that never occurred. If every configuration is equally real, and there is no preferred sequence, then the arrow of time, the direction from past to future, is an illusion arising from the way certain configurations contain records pointing in certain directions. Most physicists find this picture too extreme. The fact that our records and the physical world agree so precisely, that the correlations between memories and external evidence are consistent and lawful, seems to require that there genuinely was a past that produced those records. A universe of randomly selected configurations would not produce the kind of coherent, internally consistent record structure that we observe. The arrow of time on this more conventional view is real and requires explanation. But Barbour's challenge is valuable precisely because it forces us to be precise about what we mean by the reality of time and why we believe in it. Lee Smolin takes the opposite position to Barbour. In his 2013 book Time Reborn, Smolin argues not just that time is real, but that it is the most fundamental feature of reality. The standard view of physicists, he contends, is that the laws of physics are timeless, and that time is just one of the features of the universe that those timeless laws produce. Smolin argues that this gets things exactly backward. The laws of physics are not timeless, they evolved. They are the products of a historical process, as contingent and time-bound as the particular arrangement of galaxies in the universe or the particular sequence of nucleotides in a genome. The idea of timeless laws is a mathematical idealization, useful for calculation but misleading as a description of ultimate reality. In Smolin's view, the failure to find the arrow of time in the laws of physics is not a puzzle to be explained but a clue to be followed. The reason the laws carry no arrow is that the laws are not fundamental. Time is fundamental. The laws are derivative, evolving over cosmic timescales through a process that Smolin calls cosmological natural selection, in which universes are born inside black holes with slightly varied physical constants, and those that generate many black holes, and thus many offspring universes, come to predominate. On this account, the universe we live in is the way it is not because its laws are timeless and necessary, but because it is the product of a long history of cosmic evolution. Smolin's program is speculative and controversial, but it represents a genuinely alternative vision of how to think about time and the arrow of time. Rather than asking why the laws that are timeless happen to produce a universe with an arrow, Smolin asks what if we start by taking time seriously as the most basic and irreducible feature of the world and see what follows. The answer, he suggests, is a picture of the universe that is more open, more historical, and more genuinely temporal than the block universe picture of relativity. Neither Barbour nor Smolin represents the current consensus, if there is one. The current consensus, to the extent it exists, is something like the following. Time exists, in the sense that the temporal dimension of space-time is real and physical. The block universe picture is correct in that all moments of time are equally real in the sense of having definite physical existence. But the arrow of time is also real in the sense that there is a genuine, physically meaningful distinction between the past and future directions of time, a distinction that arises from the extraordinary low-entropy initial conditions of the Big Bang and the subsequent statistically overwhelmingly likely increase of entropy. This is not entirely satisfying as an explanation, because it rests on a boundary condition rather than a dynamical law, but it is the most well-supported picture currently available. What the research of the past several decades has added to this consensus is the growing conviction that the story is not complete. The emergence of time from quantum entanglement, suggested by the Wheeler-DeWitt equation and the Page-Wouters mechanism, adds a dimension to the story that the classical picture misses. The connections between entanglement, entropy, space-time, and the arrow of time being worked out in the ADS/CFT correspondence and the ER equals EPR conjecture suggest that time's arrow is intimately connected to the quantum structure of space-time in ways that have not yet been fully understood. And the ongoing exploration of these ideas in quantum information theory, quantum computing, and quantum gravity points toward a future in which the arrow of time is understood not as a brute statistical fact, but as a deep consequence of the quantum structure of the universe. Let us now step back and take the widest possible view of everything we have explored. The arrow of time, we have learned, is real. It is the most immediate and undeniable feature of our experience. It arises from the overwhelming statistical preference for high entropy states over low entropy states, which in turn arises from the extraordinarily ordered initial conditions of the Big Bang. It manifests in classical thermodynamics as the second law, in quantum mechanics as the irreversibility of decoherence, in quantum gravity as the direction in which entanglement grows, and in our personal experience as the structure of memory and causality and rational thought. But it is not written into the fundamental laws. The laws of physics, from Newton to Einstein to Schrödinger, are time-symmetric. The arrow emerges. It is a feature of the universe's history, not a feature of its fundamental constitution. And this emergence, which happens through the same processes of statistical mechanics and quantum entanglement that govern everything else, is itself deeply connected to the structure of quantum information, to the holographic encoding of physics on boundaries, and to the emergent nature of spacetime itself. The picture that is coming into focus, piece by piece, through the work of physicists from Boltzmann to Carroll to Penrose to Maldacena, is one in which the universe at the deepest level is a timeless quantum state, encoding all possible configurations of all possible fields in a single, unchanging wave function. Within that timeless quantum state, particular correlations between subsystems generate the appearance of temporal evolution for internal observers. The direction in which those correlations grow, the direction in which entanglement spreads and entropy increases, is the arrow of time. The extraordinary low entropy beginning that started this process of growing entanglement, the Big Bang, is the source of the arrow. And the ultimate fate of the universe, the heat death in which entanglement has maximally spread and entropy has reached its ceiling, is the endpoint toward which the arrow has always been pointing. This is a picture of enormous scope and coherence, and it is genuinely new. Boltzmann could not have imagined it. Newton could not have imagined it. It is the product of a century and a half of some of the most sustained, rigorous, and creative intellectual effort in the history of science, and it is still incomplete. The precise mechanism by which the low-entropy initial conditions of the Big Bang arose remains unexplained. The quantitative details of how the arrow of time behaves near the Planck scale, where quantum gravity effects dominate, remain beyond current theoretical reach. The relationship between the experienced flow of time and the mathematical structure of the block universe remains philosophically contested. But what has been achieved is extraordinary. We understand, better than any previous generation of scientists, where the arrow of time comes from. We understand that it is not built into the fundamental laws. We understand that it is a statistical phenomenon rooted in cosmological initial conditions. We understand its connection to information and entanglement. We have experimental evidence for T-violation in particle physics, for the Page-Wouters mechanism in quantum optics, for the quantum reversal of the arrow in controlled computational environments. We have theoretical frameworks, the ADS/CFT correspondence, the ER equals EPR conjecture, the Weyl curvature hypothesis, that connect the arrow to the deeper structures of quantum gravity and spacetime. and we have the open questions that will drive the next generation of research. Why was the Big Bang so special? Is time truly emergent from a timeless quantum state? Does the resolution of the black hole information paradox require new physics at the Planck scale? Is the block universe a complete description of reality? Or is there a genuine sense in which the future is open and undetermined? Can quantum computers tell us something fundamental about the arrow of time that classical experiments cannot? These are not empty questions. They are questions that matter, and not just to physicists. The nature of time, whether it is real or emergent, whether the future is open or predetermined, whether information is ultimately preserved or can be destroyed, touches on some of the deepest issues in philosophy, in questions about free will and determinism, about the nature of causality and identity, about what it means for the past to be fixed and the future to be unknowable. Physics does not decide these philosophical questions, but it informs them, constrains them, and sometimes transforms them in ways that open up entirely new ways of thinking. The glass falls and breaks. The equations say it could do otherwise. And somewhere in the depths of quantum gravity, in the timeless wave function of the universe, in the entanglement that weaves space-time together, in the extraordinary improbability of the Big Bang that set the whole process in motion, is the answer to why it never does. We live in the interval between the beginning and the end. We exist in the light of the arrow. And the fact that we can ask, with growing precision and growing understanding, where that arrow comes from may be the most remarkable feature of the universe we inhabit. There is one final thought worth holding as we close this journey. The arrow of time is, at its deepest level, a story about information. The universe began in a state of extraordinary information concentration, a state of remarkable low entropy in which the configuration of the cosmos was highly specific and constrained. Since that beginning, information has been spreading, diffusing, entangling, becoming encoded in correlations between subsystems that are increasingly complex and increasingly inaccessible to any local observer. The arrow of time points in the direction of this spreading. The heat death is the endpoint of this spreading, the state of maximum diffusion, the state in which no local observer can extract any further useful work from the universe's information structure. Everything we experience as time's arrow, from the cooling of coffee to the growth of entropy in stellar cores, to the aging of our bodies to the fading of our memories, is a manifestation of this cosmic spreading of information. We are not just observers of this process, we are participants in it. Our brains process information, and in doing so generate entropy. Our memories form because thermodynamic processes have written traces of the past into our neural structure. Our sense of moving through time from past to future is the result of being embedded in a universe that is moving from low information concentration to high information diffusion. To understand the arrow of time is, in a very deep sense, to understand ourselves. We are information processing systems living in the middle of the universe's great informational unfolding, capable of asking why the unfolding is happening, and beginning, at last, to find the answers. The equations have no arrow. We have one. And the story of how we got it, the story of the Big Bang's improbable beginning, and the second law's inevitable unfolding, and the quantum entanglement that weaves time itself into being, is one of the grandest stories the universe has to tell. I am Liam. Thank you for spending this time with Deep Space Intelligence. If this exploration has sparked something in you, please consider sharing it with someone who would appreciate it. Every like and subscription truly helps this channel grow, and your support means we can keep bringing you research like this, deep, careful, and genuinely curious about the universe we all share. Until next time, keep asking the questions that matter. Now let us linger more deliberately on the experimental landscape, because it is here, in the intersection of laboratory science and frontier theory, that some of the most concrete and startling recent progress has been made. The arrow of time has traditionally been a topic for theorists, because the scales at which it becomes mysterious, the cosmological scale of the Big Bang and the quantum gravitational scale of the Planck length, are not accessible to direct experiment. But that is changing. The development of quantum information technology, quantum computing, and precision quantum optics has opened new windows onto the foundations of the arrow of time that previous generations of physicists could not have accessed. Consider the 2013 experiment by Mariva and colleagues in Turin more carefully. The experimenters used a pair of polarization-entangled photons, quantum particles of light, whose polarization states were correlated in the peculiar, non-classical way that quantum entanglement allows. One photon was designated the clock, its polarization state corresponding to a clock reading. The other photon was the system whose evolution was to be tracked. The total quantum state of the two-photon system was fixed and time-independent, a timeless solution to the quantum constraint equation, analogous to the Wheeler-DeWitt equation. An external observer measuring properties of both photons simultaneously found no evolution, no dynamics, a perfectly frozen quantum state. But an observer simulated inside the system, looking at the system photon through the lens of the clock photon state, found that the system photon did evolve in time. Its polarization changed as the clock reading changed. Time flowed. The experiment was simple. It involved only two quantum particles, but the conceptual implications were enormous. Time, as an operational observable phenomenon, exists only from the perspective of an internal observer. It is not a feature of the global quantum state. It emerges from entanglement. The results of this experiment were published in Physical Review A and have been widely discussed in the physics community. They do not prove the Page-Wouters mechanism as a theory of quantum gravity. The experiment is a quantum optics demonstration, not a quantum gravitational experiment, but it validates the core mechanism proposed by Page and Wouters in 1983, demonstrating that the relational clock mechanism works in a real physical system, and it establishes a proof of concept for the idea that the familiar time of everyday physics can emerge from a timeless quantum structure. More recently, researchers have been exploring related phenomena in larger quantum systems, using quantum simulators and quantum computers to probe the boundary between quantum coherence and classical thermodynamic behavior. The central question is how the arrow of time emerges as a system grows in complexity. As more and more qubits become entangled, and the system transitions from the quantum regime where time reversal is, in principle, tractable to the classical regime where it is, for all practical purposes, impossible. The IBM quantum computer experiment of 2019 by Lesovic and collaborators, which we discussed earlier, was one landmark in this exploration. But subsequent work by other groups has extended these investigations in important directions. Researchers have shown that in quantum systems with more qubits and more complex dynamics, the probability of spontaneously reversing the arrow of time falls off exponentially with system size, precisely as the classical statistical mechanical argument predicts. The transition from quantum reversibility to classical irreversibility is not a sharp boundary, but a smooth crossover, driven by the growth of entanglement with the environment and the resulting decoherence. This experimental work is important because it bridges the gap between the abstract thermodynamic argument for the arrow of time, which works at the level of macroscopic systems, and the quantum mechanical foundation, which works at the level of individual particles and small systems. The experiments show in real time how the arrow emerges from quantum dynamics, how a system that starts in a quantum superposition and can, with enough effort, be time-reversed, gradually loses that reversibility as it entangles with more and more degrees of freedom. The arrow of time is not given by nature from the start. It grows as entanglement grows, as information spreads, as the system transitions from the isolated, coherent, reversible regime to the open, decohered, irreversible regime. This picture connects naturally to one of the most striking ideas in modern quantum information theory, the idea that thermalization, the process by which a quantum system comes to thermal equilibrium, is fundamentally an information theoretic phenomenon. A quantum system thermalizes not because it loses energy to its environment in the classical sense, but because information about its initial quantum state becomes scrambled among so many degrees of freedom that it becomes, for all practical purposes, inaccessible to any local observer. The information is not destroyed, it is hidden. It is encoded in the many-body quantum entanglement of the system, plus environment, in a form that cannot be accessed without measuring all degrees of freedom simultaneously, which is practically impossible. This scrambling of information, which physicists have studied intensively in the context of black holes and quantum chaos, is closely related to the arrow of time. The forward direction of time is the direction in which information is scrambled, in which the initial state of a system becomes encoded in increasingly complex, non-local quantum correlations. The past hypothesis, the low-entropy initial conditions of the universe, corresponds to a state in which information was not yet scrambled, in which the correlations were simple and local. The heat death corresponds to the maximally scrambled state, in which all information has been homogenized into global correlations that no local observer can extract. One of the researchers who has contributed most to understanding this connection between information scrambling and the arrow of time is Patrick Hayden, a quantum information theorist at Stanford. Hayden, working with John Preskill of Caltech, showed in 2007 that if black holes are quantum information scramblers, as the ADS/CFT picture suggests they should be, then the information falling into a black hole could, in principle, be recovered from the Hawking radiation after the black hole has evaporated sufficiently. The key result was that the recovery requires exponentially complex quantum operations and the processing of essentially all the radiation that has been emitted, but it is not in principle impossible. This was an important step in the developing consensus that black holes do not destroy information. Preskill, who has spent decades at the forefront of both quantum information theory and fundamental physics, has spoken about how the intersection of these two fields has transformed our understanding of the arrow of time. The basic insight he has emphasized is that the irreversibility we observe in the world is always a relative concept. From a sufficiently informed perspective, with access to all the quantum correlations in a system plus its environment, everything is reversible. The arrow of time arises only when we restrict our perspective to a subsystem, when we trace over the environmental degrees of freedom and work with the reduced description that is all that is practically accessible. From the perspective of the entire universe, there may be no arrow of time. The arrow is a feature of the partial view, the view from inside the universe rather than from outside it. This connects back to the Page-Wouters mechanism and the idea of time as an emergent phenomenon for internal observers. The arrow of time and the emergence of time itself may be aspects of the same underlying quantum information theoretic reality. Both arise from the entanglement structure of the quantum state. Both are features of the internal subsystem perspective, and neither is present in the global external view. Time and its direction are, together, emergent properties of the internal structure of a timeless quantum universe. This is a remarkable intellectual position to have arrived at. In the 19th century, the arrow of time was a puzzle about heat engines and gases. In the early 20th century, it became a puzzle about statistical mechanics and the nature of probability. In the mid-20th century, it became a puzzle about cosmology and initial conditions. In the late 20th century, it became a puzzle about quantum mechanics and the measurement problem. And in the 21st century, it has become a puzzle about quantum information, quantum gravity, and the emergence of time itself. Each layer has not replaced the previous ones but incorporated them, revealing that the original puzzle was pointing at something far deeper than anyone initially suspected. The philosopher of physics David Albert, who coined the term past hypothesis and has written some of the most careful analyses of the thermodynamic arrow of time, has observed that the fundamental problem is not just to explain why entropy increases in the future direction. It is to explain why we can have knowledge of the past but not the future, why we can influence the future but not the past, why causes precede effects, why records exist only of what has already happened. All of these asymmetries, he argues, flow from the same source, the past hypothesis, the extraordinarily low entropy initial conditions of the Big Bang. Remove the past hypothesis, assume that the initial conditions of the universe were typical rather than special, and all of these asymmetries would disappear. We would have no memories, no causal agency, no records, no arrow. We would have a universe in thermal equilibrium, with fluctuations occurring randomly in both temporal directions, and no observer capable of recognizing the difference. The fact that we exist, that we have memories and agency and experience times arrow, is thus, on this view, a direct consequence of the improbability of the Big Bang. We are the products of that improbability, sustained by it, defined by it. Every time you remember the past rather than the future, every time you feel that causes precede effects, every time you experience the present moment as moving toward rather than away from the future, you are experiencing the long echo of a beginning that was so extraordinarily ordered that its statistical implications are still unfolding, 14 billion years later, in the structure of your thoughts. There is something humbling and something exhilarating about this. Humbling, because it means our deepest and most immediate experiences, the flow of time, the structure of memory and causality, the very architecture of rational thought, are contingent on an initial condition that the laws of physics did not require. They arose because the universe happened to begin in a particular way, not because any law demanded it. Our experience of time is, in the most fundamental sense, an accident of the beginning. Exhilarating, because it means we live at a special moment in the history of understanding. We are the first generation of beings on this planet who can say, with reasonable confidence and good evidence, where the arrow of time comes from, what drives the second law, what the connection is between quantum entanglement and temporal experience, and what the ultimate fate of the arrow might be when the universe reaches the end of its long thermodynamic unfolding. We do not have the complete answer, but we're asking the question with more clarity, more mathematical precision, and more experimental grounding than any previous generation. That is what science does at its best. It takes the most obvious features of reality, the things so immediate that we rarely stop to question them, and reveals them to be connected to the deepest and most hidden structures of the cosmos. The arrow of time is the most obvious feature of reality there is, and it turns out to be connected to everything, to the Big Bang, to quantum entanglement, to the nature of space-time, to the structure of information, to the meaning of causality and memory and knowledge. There is nowhere to go in the investigation of the arrow of time that does not lead to something profound. The equations have no arrow, and yet we do, and the story of how the second of those facts arises from the first, when the universe is understood deeply enough, may be the most beautiful story in all of physics. To complete our journey, it is worth examining the arrow of time through one more lens, one that is perhaps the most intimate and human of all the perspectives we have considered. The arrow of time is not just a feature of the physical world, it is the defining structure of a human life. It shapes everything about what it means to be a conscious being moving through the world, and understanding it changes how we might think about existence itself. Consider what it means that entropy increases. It means that ordered structures, left to themselves, naturally tend toward greater disorder. Living organisms are remarkable exceptions to this tendency, but only locally and temporarily. A living cell maintains its internal order by consuming free energy, by taking in low-entropy chemical inputs and releasing high-entropy waste, effectively exporting its entropy to the environment. Life is not a violation of the second law. It is an extraordinarily clever way of exploiting the second law, of channeling the flow from low entropy to high entropy into the creation and maintenance of local order. And when life ends, when the organism can no longer import free energy and export entropy, the second law reasserts itself. The ordered structures of a living body decay. Entropy rises. The arrow of time, for that particular structure, has reached its local endpoint. This is not a morbid observation. It is a profound one. Life exists because the universe began in a low-entropy state and has not yet reached equilibrium. The vast entropy gradient between the early universe and the heat death, the enormous thermodynamic potential that the Big Bang created and that has been slowly releasing ever since, is what makes life possible. We exist in the sweet spot of that gradient, where the entropy is high enough to allow complex chemistry and low enough to allow ordered structures to persist for billions of years. The arrow of time does not just point in the direction of our deaths, it is the reason we were born. The same is true of consciousness, of thought, of experience. The brain is an extraordinarily efficient information processing system, and information processing, as we learned from Landauer, generates entropy. Every thought you have, every memory you form, every decision you make involves the erasure and rewriting of information in neural circuits, and every such operation generates a tiny amount of heat. Your mind operates along the arrow of time, not just as a feature of its subjective experience, but as a physical process that participates in the universe's inexorable march toward higher entropy. You're not just an observer of the arrow, you're a physical expression of it. This has a curious implication for the experience of time itself. The sense of the present moment, the sense of now, of being here at this specific point in time rather than at any other, is something that no physical theory has fully explained. The block universe tells us all moments are equally real. Statistical mechanics tells us about the direction of the arrow, but neither addresses the phenomenology of the present, the specific visceral immediacy of this moment compared to all the others. Philosophers have wrestled with this for centuries, and physicists have generally considered it outside the domain of physics. But some researchers, including Carlo Rovelli in his book The Order of Time, have suggested that the sense of the present might itself be connected to the arrow, to the thermodynamic fact that this particular moment is the one at which our internal information processing systems are currently interacting with the world. The present is not a feature of space-time. It is a feature of an information processing agent's relationship with the thermodynamic flow of the universe. Rovelli has been one of the most eloquent and thoughtful writers on the physics and philosophy of time in recent years. In the order of time, he argues that time as we commonly experience it, as flowing, as directional, as divided into past, present and future, is not a fundamental feature of the world, but an emergent one. At the fundamental level of loop quantum gravity, the approach to quantum gravity that Rovelli has helped develop, time does not appear in the basic equations. Events are not ordered by a universal time coordinate. The universe is a network of quantum gravitational interactions, and what we call time is a macroscopic approximate description that emerges when you coarse-grain over the microscopic quantum gravitational degrees of freedom. In loop quantum gravity, space and time are not continuous backgrounds but discrete, quantized structures woven from fundamental quantum elements called spin networks and spin foams. The dynamics of these structures do not unfold in an external time. They are constituted by the relations between adjacent quantum elements. Change is not motion through time. Change is the transformation of these relational structures, and what we call time is a description of that transformation from a macroscopic perspective, a description that smooths over the quantum discreteness and produces the continuous time dimension of classical physics. This approach to quantum gravity is different from the string theory-based approach that underlies the ADS/CFT correspondence and the ER equals EPR conjecture we discussed earlier. The two approaches, loop quantum gravity and string theory-based quantum gravity, represent different research programs with different strengths and different open questions. Neither is complete. Neither has been experimentally tested in any direct way. But both point in the same direction on the question of time. At the fundamental level, time is not given. It emerges. The convergence of these very different theoretical approaches on the same general picture of time as emergent is itself significant. It is the kind of convergence that suggests the picture is tracking something real about the structure of nature, even if the details of any particular theoretical implementation remain uncertain. When approaches as different as loop quantum gravity and string theory-based quantum gravity both conclude that time must emerge from something more fundamental, the conclusion carries more weight than either approach alone would provide. And what does the emergence of time from quantum gravity tell us about the arrow of time? It tells us that the arrow is not just a statistical feature of macroscopic systems. It is connected to the most fundamental level of physical description. The direction in which time flows, the direction in which entanglement grows and entropy increases, is the direction in which the quantum gravitational substrate of spacetime is becoming more complex, more entangled, more configured in the sense needed for an internal observer to have experiences and form memories. The arrow of time and the emergence of time are two aspects of a single, deep physical reality. The unfolding of quantum gravitational correlations from simple, low entropy, low entanglement initial conditions toward complex high entropy, high entanglement final conditions. This is, perhaps, the most complete picture we currently have of where time's arrow comes from. It is incomplete. It rests on theoretical frameworks that have not been fully developed or experimentally tested. It raises questions that it cannot yet fully answer about the nature of the initial quantum gravitational state, about the mechanism by which low entropy initial conditions arise, about the detailed structure of the transition from quantum timelessness to classical temporal experience. But it is the direction in which the best current thinking is pointing, and it is a direction of extraordinary richness and depth. As we bring this exploration to a close, it is worth returning to the most fundamental paradox with which we began. The laws of physics are time-symmetric. The universe is not. This paradox, which seemed at first like a technical puzzle in statistical mechanics, has revealed itself to be a window onto some of the deepest questions in all of science. Questions about the origin of the universe, about the nature of quantum mechanics, about the structure of space-time, about the connection between information and physical reality, about the meaning of time itself. The answers. We have found are partial but genuine. The arrow of time arises from the interplay of time-symmetric laws and extraordinarily special initial conditions. It is reinforced and manifested at every level of physical description, from the collisions of gas molecules to the growth of quantum entanglement to the evolution of the cosmos. It is not a fundamental law but an emergent phenomenon, one that requires both the physics of statistical mechanics and the cosmology of the Big Bang to be properly understood. And in understanding it, we understand something profound about ourselves. We are creatures of the arrow. We exist, we think, we remember, we anticipate, we love and grieve and create, because the universe began in an improbable, exquisitely ordered state, and has been spending that improbability ever since. The arrow of time is not a constraint imposed on a timeless universe. It is the universe in the act of becoming, and we, briefly and brilliantly, are part of that becoming.